today are Animesh Day, Chief of Product Development here at VEXTEC, Emmanuel De Leon from the Air Force Lifecycle Management Center, Propulsion Directorate at Tinker Air Force Base, and Bob Tryon, Chief Technology Officer at VEXTEC. We'll be speaking on the current challenges associated with qualification and certification of metal AM products, particularly in critical applications such as aerospace and how model-assisted techniques using integrated computational materials engineering, or ICME, can augment the standard practices in the certification process. First off, Animesh will speak a little bit about VEXTEC, how our clients utilize us, and give a brief look at some of the current gaps within the AM strategy regarding understanding reliability, risk, and qualification and certification, or Q&C for short, and how modeling techniques can help fill those gaps. He'll also touch on recent SBIR work that we've done with the Air Force's Rapid Sustainment Office on developing an AM ICME framework tool, and introduce follow-on work that has been initiated with the Air Force Lifecycle Management Center. Next, Emmanuel will take us through a demonstration case that VEXTEC and AFL-CMC jointly undertook, an evaluation of a possible AM replacement for a legacy aero engine fuel-controlled bell crank component. He will set up the problem and the data that was originally available to AFL-CMC. And then Bob will describe the modeling steps that we undertook at a broad level, both in the structural analysis as well as in ICME. And we will look at the modeling prediction results, where no specimen or component testing had been performed beforehand, and how they compare between conventional and AM materials. And I'll rejoin at the end to discuss some of the analysis of the predictions and conclusions, as well as where we can go from here. We would like to acknowledge Dr. Howard Sizek at the U.S. Air Force Rapid Sustainment Office for the support in this work. And with that, Animesh, I'll hand it over to you.
Thank you, Mike. So as an introduction, Dextex is a software as a services company. We're out of Nashville, Tennessee. Our software product, VPS-MICRO, is a computational tool to predict the risk of metal fatigue failure. The value proposition for using VPS-MICRO is to supplement physical testing with computational data for increased confidence. The goal here is to have a mix of physical test data combined with virtual data to accelerate the qualification and certification process, especially for structural AM parts. Over the past 2 decades, we have successfully helped over 150 clients across multiple industries, ranging from aerospace to medical devices, where risk and the consequence of fatigue failure can be high. Our technology has matured and has been validated through several Department of Defense programs, and we hold 7 U.S. patents. So taking a slightly closer look at how our clients benefited, specifically VPS-MICRO has been successfully used in qualification of new materials. Often this is referred to as second sourcing in the conventional manufacturing parlance. In a similar vein, recently our clients have also used the tool to certify AM materials. It is analogous to second sourcing, where we're attempting to replace the original cast or forged material with an AM variant. Also, because the software tool is probabilistic and uncertainty-based, through simulation, it has also been used by clients to identify rare fatigue failure issues that may not have been uncovered during regular testing. Now, we all recognize, metal additive manufacturing has its own challenges. These are things that we all acknowledge. To mention a few, it's, AM requires often a redesign of the part as it is being built to accommodate the build process. So it can result in different load paths and thus, different stress profiles which need to be accounted for in the analysis. In addition, because of the flexibility offered, in terms of multiple build parameter options and related heating cooling issues, the AM material itself might have different, microstructural properties, strength properties, textures, and such, which require that new design allowables be developed for AM material. We understand, I think, recognize, post-build treatments, surface effects, surface roughness can play a significant role. When all of these real and legitimate issues make this qualification and certification for AM an iterative process. So these are known facts. The consequence of this iterative process is it makes the whole paradigm, lengthy and thus costly. On the top right, I'm sharing a graphic from DARPA, actually, which illustrates this point. And you will all agree that the cost of iteration increases later in the design cycle that such issues are identified. So the challenge here is, how do we accelerate the certification process without sacrificing any of the required accuracy? And especially for AM, this is a challenge because, compared to conventional methods where there's significant past experience, data, and knowledge base for forging and casting methods, AM is, relatively speaking, a very new manufacturing method in terms of its adoption in the current day and time. And so to accelerate the process, what we're proposing is we supplement testing with computational methods and develop a qualification and certification process. Now, when we talk about a computational certification process or an ICME-based certification process, we're not advocating that we change the required elements of the process. Instead, what we are saying is we start simulating important, relevant aspects of that process and see how that can be used to accelerate. For example, we can build and we can gather data from the building process and develop a 3D model of the local material microstructure. We can use that model and feed it into part performance simulation and simulate what would happen if the part were to be tested. And we say only test when one develops a high confidence that that test will be successful. So thus we're kind of reducing some of the actual iterative time and cost associated with this build and test paradigm. And in the process, we actually can have a model where we're linking the AM build process to the resultant microstructure and then taking it all the way to part performance. And this can have an important benefit for legacy parts where quite often, the original drawings and the analysis may not be readily available. So next slide, please. So the specific example we're going to talk about today is part of a U.S. Rapid Sustainment, U.S. Air Force Rapid Sustainment Office SBIR project. The goal here was to demonstrate how we can build a computational framework to link various elements of the AM build process, the part evaluation and inspection process, and finally simulate part performance. And there are models and computational tools and sensors available in each of these individual areas. What we need is to determine and demonstrate what is necessary to link these various tools and regimes to one another in a logical sense. Our partners in this project were UDRI and Arctos, and they provided valuable knowledge and tools to link this computational tool to VPS-MICRO. In this program, we also got the opportunity to demonstrate how simulation can be used to determine if an AM material is a suitable candidate before even one attempts to go through the rigorous build and test protocols. And that's an important aspect. One needs to kind of gain confidence that the AM material is going to be a suitable candidate and can perform as good as, or if not better than, the original metal material. We worked with the Air Force LCMC Center at Tinker, and later Emmanuel will speak about the details of the project. You will see how the method was applied to a legacy part. So with that brief introduction and the context, I will turn it over to Emmanuel, who will give you additional details and specifics about the project. Emmanuel, yours.
Thank you, Animesh. And again, I had the opportunity to work with Animesh and his team at VEXTEC to evaluate the Air Force's ability to integrate AM components in our propulsion platforms. We saw with this, however, came with technical challenges we have to overcome in order to properly implement the technology. It is the Propulsion Directorate's goals to organically manufacture AM components, as well as gain overall confidence in the integration and performance of the AM components when compared to its conventionally manufactured equivalent. With these goals in mind, we were able to demonstrate these two goals with an example candidate belt crank. Slide, please. The procedure we went through for modeling and analysis, including selecting the belt crank from a list of identified candidate parts from the Air Force, gather any available technical data we had in our depository, develop a CAD model of the belt crank using the gathered data, and perform structural FEA simulation. For the study, we used ANSYS for the FEA. Then finally, we imported these results into VPS-MICRO with material data to simulate fatigue performance. Slide, please. The VPS-MICRO software requires design and material inputs to completely simulate component failure statistics. The design inputs were coming from CAD and CAE, and material data was available from published or available values. A critical advantage of using VPS-MICRO is that the design analysis only has to be performed once. This is important for AM because material analysis comparisons can seamlessly be performed between the AM material candidate and its raw material. With the AM material, however, additional data may be required and necessary based on its application and risk of failure in the engine. Slide, please. So for the belt crank, the data was comprehensive enough for demonstration purposes in VPS-MICRO. We were able to identify major dimensions and raw material information in the belt crank drawing, as seen on the left. And on the right, in those group of photos, we were able to identify its application to its power control assembly on the engine, which was helpful for us in understanding the loads applied to the component. Slide, please. And with the gathered data, we moved on to producing a CAD model of the belt crank using SolidWorks. And again, major dimensions were available from the drawing. However, a few geometrical features were not explicitly shown. And when comparing it to an actual belt crank provided by our propulsion directorate, the CAD model was good enough to perform the required analysis without overall loss of information for the purposes of this demonstration. And now Bob will go into further detail about the analysis of the belt crank.
Thank you, Emmanuel. So once the geometry is modeled using the CAD, we need to look at the boundary conditions before we can build the final model. And after reviewing the assembly drawings, the engine photos, we talked to the equipment specialists to determine the maximum and minimum orientations of the belt crank linkage. And then using free body diagrams, we determined the loading direction for the max min and several intermediate orientations. Then using mechanics materials, we determined that the maximum tensile load in the assembly is about 2,300 pounds, which is governed by the yielding of the upper rod. And the maximum compressive load in the assembly is about 182 pounds, and that's governed by buckling of the lower rod. And then if we take basically a +3 sigma load that a pilot could apply through the power lever, that would impart about 45 pounds in the assembly. So, slide. So we created the FEA in ANSYS by meshing the CAD model and applying a unit load for each of the orientations on the previous slide. The 40-degree orientation showed to have the maximum stress and the most stressed volume. Now keep in mind that the AM process can produce different material at different locations depending upon thicknesses and various other things, or orientations. So one of the other orientations could become the limiting factor, and once we were to build the part, we could cut it up and look at it and see if we need to look at one of the other orientations. But for this demonstration, we'll go choose the 40-degree orientation. As far as the material goes, the legacy belt crank is a stainless steel, cast stainless steel, and the proposed replacement is AM cobalt chrome. Now, we didn't, for this demonstration, we didn't have material test data directly from either the legacy or the AM part. The idea is to simulate the performance before we invest in laboratory work or build actual parts. So we used previously available data sets for both materials, and those data sets for the cast stainless steel legacy part came from an article in the International Journal of Fatigue, and so a similar data set for the AM cobalt chrome, and that was from the journal Materials. And what this table shows is the inputs that go into the VPS-MICRO fatigue software, and these inputs include the standard monotonic and cyclic stress data. The other thing that goes in there is statistical distributions of microstructural features, which we gathered from micrographs that are, some examples are provided on the right-hand side of the slide. So what this slide shows is basically smooth round bar fatigue SM plots. And so the simulated data is the colored dots, and there's a plot there for both the AM cobalt chrome and the legacy stainless steel. And the reason there are many data points for the model predictions is that we simulate multiple specimens at each stress level. The microstructure for each specimen is generated using Monte Carlo simulation and has statistically varying microstructure. So each specimen has a unique fatigue life just as in actual test. Now, before we got to these plots, we calibrated the fatigue model using one fatigue data point at about 80% of the monotonic yield strength. And that point was pulled from the references. And then basically that calibration is shown here. And the other data available in those references are the black X's. Those black X's are the actual data for those materials. As you can see, the model does a good job of capturing the average and the scatter and the fatigue lifetimes for both the AM cobalt chrome and the stainless steel. The next slide. So after we've got that calibrated model, we use the FEA to capture the geometry and the stresses of the belt crank. In this case, it's a 40-degree orientation. And then we can simulate a laboratory testing of many bell cranks at different applied loads. And we do this because we take the microstructure for each simulated bell crank is generated using Monte Carlo, and therefore it has statistically varying microstructure, so each bell crank in the test has a unique life. For this example, we chose spatially consistent properties, but we could choose to vary those properties at different locations on the bell crank. The black circles here are the simulated stainless steel bell crank, and the red circles are the AM cobalt chrome bell crank. And as you can see, the simulated AM cobalt chrome bell crank's fatigue strength is lower than the simulated stainless steel bell crank. Now, remember, these simulated results are to help us decide if we want to pursue cobalt chrome as an available replacement for the stainless steel in the bell crank, but we want to do that before we've actually built any replacement parts. And as this chart is showing us, our simulated AM cobalt chrome bell crank has lower fatigue strength than the legacy bell crank. So we need to revisit the loads analysis. And for that, I will hand it back over to Mike.
Okay, thanks, Bob. So how we apply this simulation data to the Q&C process for consideration of an AM replacement is we can evaluate this virtual output data in terms of probability of failure. So as you see here, the cobalt chrome bell crank's fatigue strength is lower, as Bob mentioned, but it's still much higher than what the pilot would be able to impart to that bell crank. So in this demonstration case, an AM replacement bell crank, although it has lower fatigue strength, would still not be expected to fail in fatigue due to the constraints that the pilot has in terms of the amount of load that can be placed on that bell crank through those connecting rods. So the next steps that would be ahead of us, if this part was determined to be fatigue critical, would include destructive metallurgical analysis of a used conventionally manufactured bell crank, as well as metallurgical analysis of a similarly sized candidate AM specimen. So then we would work to calibrate the material model using the newly acquired testing data that we did perform, and calibrate that to fatigue testing and validate the model performance against these different testing conditions. So what conclusions ultimately can we draw from this demonstration analysis? It's really without having a priori component physical test data, conventional or additive manufacturer data, VPS-MICRO was able to simulate the relative fatigue reliability between the conventionally manufactured bell crank and a proposed AM variant for sustainment, to meet sustainment goals. So in summary, what we spoke about today was applying ICME-based modeling methods to understand the performance of a candidate AM replacement for an aero engine bell crank. And this type of analysis can provide engineers with additional information prior to a physical build test paradigm, which can often be the bulk of a certification process, both in time as well as in cost. So that wraps up kind of our prepared slides. I did want to provide a brief plug of the upcoming America Makes MMX virtual event coming up in a few weeks, December 1st and 2nd. VEXTEC will be there with a virtual table, and we'd very much like to network with you. It is free to register for this two-day virtual event, and it's available, the registration is available at the America Makes website that you see in the bottom right-hand corner of the slide here. And you don't have to be a current America Makes member, nor does your organization have to be a member of America Makes to attend this event. So we would look forward to seeing you there. It'll be the first week of December. And we do appreciate your time today, and we're happy to take any questions that you have at this time. Nick, I'll turn it back to you.
That's come up is what do you do when you have
Nick, are you on mute?
I wasn't, but I'm having a little bit of technical difficulties. Can you hear me now?
Yes, yes we can.
Okay, thank you. Sorry about that. I mentioned thank you for the presentation and the MMX reminder, and I would like to invite any attendees to type questions into the Q&A section of your screen, bottom right corner. There should be an option there. One question we have for you is, what do you do when you have limited loading data for a legacy part?
Well, this is Bob speaking here, and one of the things is that indeed, if your replacement part has better fatigue capabilities than your original part, well, then you can, I don't know how to say it, but then you can, you feel pretty confident that if your original part did not fail from fatigue, your new part is better, and therefore you wouldn't expect it to fail from fatigue either. But if you've got a similar or lower fatigue capability of your AM part, then you're going to have to step up to the plate. I don't know any other way to do it, and actually get some good load state, either experimentally putting some strain gauges on, which is something we do a lot around here, or go back and do you do a thorough loads analysis and geometric analysis on that part. Now, given that there are a lot of good hardware and software combinations that allow you to capture geometry as far as blue light and white light, but you still have to buckle down and do that loads analysis.
Okay, thank you. How about this? Does the model's prediction incorporate location-specific properties?
Yes, the model can, and through the FEA, you can actually, at each element at the FEA, if you had such fine properties, you can allow the properties to change by putting the properties in the FEA and assigning them to particular elements in the FEA, and depending upon the stress and the volume of those elements, that it would capture that. You could also do things like surface roughness. If you had a machine, if part of your surface was machined and part of it wasn't, that can be put into the model also, again, using the final model as your source of applying the spatial dependency of those properties.
Right, and I'll just follow on to what Bob said, is that VPS-MICRO doesn't operate within the FEA framework, but we do take information from the FEA in an element-by-element sense. And so those, if there is material differences in specific locations on a component, those can be mapped to certain FEA element numbers, and those can be assigned different material properties within the VPS-MICRO simulation.
Okay, thank you. Here's another one. For that study that you just did you actually build any of the AM parts?
No, there were no AM parts built for this study. Now, the Air Force does have a lot of data on cobalt chrome, and we didn't show any of that either. So there's been a great deal of work on cobalt chrome itself and getting material properties, but none of these parts have yet been built.
Okay. And how about, does the FEA remain valid for potential variation in the material itself? Or is it the analysis valid?
Right, that's a good question. That is a question more for the structural analysis group of whether or not the variation in the material would be appropriately captured by the FEA. So that is something that as we said before, VPS-MICRO can differentiate at that level of granularity, but whether or not the FEA is valid for different materials, that would be an item that
We can handle it.
right, that's something that can be handled.
I mean, if there is a variation in the material property, let's say texture, which leads to, you know, the modulus change, one can change the modulus of the material. And again, that can be a location-specific change and put into the model to get the resulting, you know, predictions here. So indeed, if there is a material change that leads to, you know, a different stress profile, it can be handled.
Okay, I don't see any further questions in the Q&A. I'm posting the Mike's email address in case anyone has any further questions afterwards. I'm also going to post, I posted that to the chat, hopefully that showed up. And if anyone is interested in presenting at a TRX webinar, there should be a form that pops up right after the presentation here that will allow you to apply for that, but you can also reach out directly to the coordinator for the TRX webinar series, which is Jason Thomas, and I just posted Jason's email to the chat. Beyond that, that wraps up today's TRX webinar series. Thank you very much to the VEXTEC team once again. We really appreciate it. And I would like to wish everybody a great day. Thanks for joining us.
Thank you all.
Thank you all. We appreciate it.
Thank you.